All right, let's wrap up with this question here. It says the accompanied, shouldn't it be accompanying? I'm not sure. Accompanying figure shows an arrangement for measuring mass of ions, and this is question 107. Mass of ions by an instrument called the mass spectrometer. Yeah, sounds right. The particles come out over here. They bend under magnetic field. The path bends under magnetic field. They hit something here. An ion chamber. The ion is accelerated by potential difference, delta V, right? And allowed to enter a region of constant magnetic field. This is quite similar to the charge to mass ratio apparatus that you will be seeing in lab very soon. I mean, you know, this is probably more sophisticated than that, but the operating principle is the same. Constant magnetic in the uniform magnetic field region, so semicircular path, striking a photographic plate at a distance x from the entry point. Derive a formula for mass in terms of B naught, Q, delta V, and X. Let me just note a couple things to simplify things. What they are calling X here, this is basically diameter, which is, you know, 2 times the radius of this circle. Just acknowledge that, because the expression I'll have is for basically the radius of the path. This is why in the mechanics review earlier in the semester I had you review circular motion. Here the magnetic force, so from the path this ought to be the direction of magnetic force. Let's just double check to be sure. So, you know, the V going this way, so for the point I picked, this is the direction of V. So V going that way, magnetic field is coming out of the coming out of the screen. Yeah. V cross B, and the thumb is pointing kind of you know, right and lower in the direction I did F cross B. So it's a positive ion, right? You might not say, but it's a positive ion. Should be. Let me double check from my perspective. Yeah, positive ion. So in this circular motion, this is what you can say. So if you are imagining a free body diagram that looks like this, I'm imagining looking at this from a vantage point of observer looking from here. Then I have a magnetic force that's pointed this way, and this should be my centripetal force, which is from circular motion kinematics, mass and Newton's second law, mass times V squared over R. I have a formula for magnetic force from the chapter that's equal to absolute value of for the magnitude Q V cross B, and I think here everything's arranged so that V is in the plane of the screen, B is perpendicular to the plane of the screen, so this cross product just gives you the product of the magnitudes, no sine theta to worry about. So I can say this is equal to the right hand side. Let's just write it out. In terms of the symbols I have, is there a V naught here? Oh, I don't have a V naught. Instead, what I have is I'm given the accelerating potential difference. So I need to solve a mini problem here to figure out what my V is as it exits that region. So here I use conservation of energy. I'm gonna simplify it. You know, let's say I start out with some amount of potential energy here. By the time particle gets to this point, all of the potential energy is gone. You only have kinetic energy, and from conservation of energy, you say these two are equal to each other. So you say the amount of potential energy, which should be amount of charge times the accelerating voltage. Let me use delta V as the question does. I say that is equal to the kinetic energy, 1/2 m the lowercase v naught squared. So let me just solve this for V. I think that's going to be simple enough. Solving it for V, the squared version first, that would be 2 times Q delta capital V divided by M. I need to take square root for the V naught. So I'll be using this expression after I'm solving for mass. After I solve for mass. So let me go back to my original question here and solve this expression for mass. So I have mass is equal to move v squared over r over to the other side. Then I have r times q times v naught b, b naught, v naught b naught divided by v naught squared. Some factors cancel. I guess I can cancel one factor of this with that. And for v naught, I can now put in this expression that I derived. And as I'm doing that, let me rewrite r in terms of, I think I have to write it in terms of x. So r is the radius of curvature. Is going to be the x divided by 2. So x divided by 2 times the amount of charge times b naught divided by square root of 2 times the accelerating voltage setup arrangement. Oh, I probably should have plugged in mass first. This is yeah, let me actually do that. So this is the kind of problem with solving for an unknown prematurely before you've eliminated all the unknowns. I forgot my v naught, it's a function of m. So when I plug this in, it introduces m here. So really, so you know, I tell stuff to do this and I forget myself. So and I tell people to approach your problem solving systematically. And the systematic way to approach it is, one, you first count what you have before you start doing a bunch of math. So let me write down a simplified version of this expression here. Q v naught b is equal to m v naught squared over, let me just put in x over 2 now. So this is my equation 1. This is my equation 2. And I ask myself, how many unknowns do I have? Q I have, v naught I don't, that's one unknown. M I don't, I'm solving for it, that's 2 unknown. V naught already counted, x I have it. V naught already counted, all this I have it, I don't have m. So 2 unknowns, 2 equations, I can solve it. So here, now you have to decide which unknown to eliminate first. Since I only want m in the end, I'm going to eliminate v naught. And for that, I need to solve one of those for v naught. Conveniently, that's done already. Use this as tool to eliminate v naught from all my equations. So here, I can either plug in v naught both here and here, or I can pre-simplify this a little bit, canceling this out. Then I can just plug in this v naught here. Let me write that down. QB is equal to m divided by x over 2 times the v naught, which is square root of 2q delta v divided by m. And the advantage of this approach is that you avoid going backward by reintroducing the m known that you already solved for here. So what I can do is I can imagine this m is actually m squared then square rooted. Then they are now both under the square root. I can cancel this factor of m with the one factor of m here. So let me solve for square root of m. It's on the side it's gonna be on. Then move the rest to the other side. It's gonna be so QB times x over 2, having moved this over, and then divided by square root of 2q delta v. To solve for m, you just take this whole thing, square the whole thing. That'll give you m is equal to qb x over 2. Let me just square this all together. Divided by, now I just get rid of the square root, 2q times delta v. Now here I can simplify it a little bit, you know, cancel some factors of q. Not strictly necessary, unlike here where it was strictly necessary to be able to solve for m. But from here, you know, I'm satisfied enough that everything on the right hand side here is in terms of known quantities, so I can just plug in the numbers, you know, bring up O from alpha and plug in the numbers. Let me do that. Yeah, plug in the numbers. All right, Q that oh wait, am I plugging in numbers? No, they are looking for algebraic expressions. So let me just type it in. Sorry, didn't need O from alpha. Q times I think it's a B naught. Let me just double check to be sure. under vars, yeah, b naught times, and yeah, x divided by 2. Let me make sure I put parentheses around the whole thing. That squared divide, that divided by 2 times q times, and is delta v one of my variables? Yeah, delta v. Yeah, good. All right, I think I do need to scroll down to click submit. Yeah, let me scroll down and click submit, and I'll scroll back up. Good. Yeah, that's correct. Yeah, I got confused with maybe there was a number, but no number needed. So so this is like an experimental setup where the main thing you would be measuring is basically x. You move your detector until you can detect the particles that comes back. With the parameter x, you plug it in here. Then with everything else known, you get the mass of the ion, assuming you know its charge.